Okay, I think we're ready to start. So welcome everyone. This week's, we're very lucky to have Andrea Puhm with us, who's going to be telling us about a double copy for celestial amplitudes.
Thanks very much for inviting me back to Cape Town virtually. I think we're about 10,000 kilometers or so apart, but very conveniently located in the same time zone. So that's great. Okay, so I'm going to be talking about celestial amplitudes and these remarkable relations between gauge and gravity amplitudes, which are known as double copy. And this is based on work from July in collaboration with Eduardo Casali from UC Davis. Okay, so it turns out that there exists a conformal basis for quantum field theory scattering amplitudes. And this arises by replacing the asymptotic states, which we usually take to be plane waves, by so-called conformal primary wave functions. And that's possible because the four-dimensional Lorentz group, SO1,3, or SL2Z, acts as the global conformal group on the two-sphere at null infinity of asymptotically flat space, namely the what's called the celestial sphere. And the consequence of this is that four-dimensional scattering amplitudes, depicted here for some massive scattering process, can be recast as two-dimensional conformal correlation functions where operators are inserted at the celestial sphere. Now, one motivation for studying scattering amplitudes in this new basis that makes these conformal properties manifest is that they could provide powerful constraints on the quantum gravity S matrix when recasting this basis. And we already have some examples of that in the form of factorization theorems. Another motivation is that by recasting scattering amplitudes in a different basis, we might get new insight into certain fundamental structures of amplitudes, such as, for example, the double copy, which I will talk about in detail. Now, there is another motivation besides this interesting aspect of studying quantum field theory from a different perspective. And this arises because celestial amplitudes make conformal properties manifest. And so this opens the window for attempting to construct a holographic dual to quantum gravity in asymptotically flat space. We already know of examples like this in negatively curved space, in anti-de Sitter space, and to some extent also in spacetimes with a positive cosmological constant. Now, what's particularly nice in anti-de Sitter space is that the confining boundary conditions make it act like a box. And so we can study quantum gravity in anti-de Sitter space as an isolated system. And this has given rise to the remarkable ADS-CFT duality, where there's a conformal field theory living on the time-like boundary of anti-de Sitter space. Now, for de Sitter space, there exists also some holographic structure, but it's more mysterious because unlike in ADS, where space seems to be emerging, now we have the notion that time seems to be emerging. And while holography in anti-de Sitter space has given us a lot of insight into structures of quantum gravity, and in particular black hole physics, this is not the spacetime that describes our universe. It does describe very well the spacetime near highly rotating black holes, but that doesn't describe most of our universe. And while at the cosmological scale, we would be interested in holography for de Sitter space, this is a bit more mysterious, as already mentioned. And so in between those two scales, there are vast regions of the universe where space-time and physics in it is very well approximated by asymptotically flat space. And so a natural question to ask is if there is an underlying holographic structure in asymptotically flat space. And this is somewhat different from the holographic structure in anti-de Sitter space. For one, we have radiative space-time where stuff leaks out through null infinity. And so the question is there a holographic setup? So the first question that you would want to answer, much as what has been done in anti-de Sitter space, is what are the symmetries of the space-time so that you can identify a proposed holographic dual. So here, this question has had a long history and a very controversial one at that. But what has come out of much revision over the last couple of years is that the Bondi-Metzner-Sachs, or BMS group, seems to play a fundamental role in describing the symmetries of asymptotically flat spacetimes. And there exists an extension that includes a Virasoro asymptotic symmetry or a full diffeomorphism group of the celestial sphere. Once you have settled this question, then you can ask where would a proposed holographic dual theory live? And the natural place for it to live is the conformal boundary of asymptotically flat space, namely null infinity. And what has been shown in the past couple of years that amplitudes, when manifests conformal and certain limits of scattering amplitude. Is there a background noise? Okay. Certain limits of scattering amplitudes give rise to structures that we know in two-dimensional CFT. So for example, the collinear limit of scattering amplitudes gives rise to the notion of OPE singularities, of two-dimensional conformal correlators, and energetically soft theorems, which are important in quantum field theory as they give rise to universal factorization theorems, can be recast as statements about conformal correlators and how they factorize. More recently, the study of quantum corrections has been addressed, and it turns out that loop amplitudes seem to be obtainable from tree-level celestial amplitudes by the action of certain operators, and I will comment a bit more on that at the end of my talk. Now, at Strings, I talked at length about asymptotic symmetries and how this gives us insight into a possible flat space holographic picture. And Andy Strominger talked a lot about OPE singularities and other aspects of celestial amplitudes. So I will not talk more about these aspects, but instead I want to focus on fundamental properties of amplitudes, in particular the double copy relation and how it shows up in celestial amplitudes. Okay, so double copy in one slide. The slogan is that gravity is a square of Young-Mills theory. And there are many examples of this statement and generalizations of these statements, whose references I cannot all list here, but there was a review last year that can be consulted for that. So for the purpose of this talk, I just need a few ingredients. So we start with an endpoint Young-Mills amplitude, which is given by an energy momentum conserving delta function, and then a sum over graphs with some propagators pi. There are some color factors C, and then some kinematic numerators N. And these color factors here, they satisfy a Lie algebra Jacobi identity between the S, T, and the U channels. And at tree level, one can always find kinematic numerators N that mimic this relation. These are called color kinematics dual or BCJ numerators. And upon replacing in the Young-Mills amplitude these color factors C by another set of kinematic numerators, one finds an amplitude which turns out to be nothing but the scattering amplitude for N gravitons. And so the slogan that gravity is Young-Mills theory squared is encapsulated in the squaring of these numerators. Okay, so the question that I want to address now is whether there exists a double copy notion for celestial amplitudes. And so, of course, since, as I mentioned, going from the usual amplitudes to celestial amplitudes involves a change of basis of the asymptotic states, you would, of course, expect that fundamental properties of amplitudes survive such a change of basis. But the thing is that usually when we use amplitudes with asymptotic plane wave states, the double copy makes heavy use of momentum conservation. So of this delta function in momentum. So it uses the manifest translation invariance of plane waves. When we go to celestial amplitudes, we have as asymptotic states no longer wave functions that manifest translation invariance, but we have these conformal primary wave functions which depict conformal properties, but translation symmetry is completely obscured. And so if you cannot use momentum conservation explicitly, then the question is how do you arrive at a statement that is reminiscent of the momentum space double copy. So in this talk, I will show to you that there exists a well-defined double copy procedure for celestial amplitudes, but this requires that we generalize the usual squaring of numerators. Namely, we first should promote these numerators to generalized differential operators that act on external wave functions and then square them. And I'm gonna describe this now in detail. So I've given you some motivation for why we would be interested in studying celestial amplitudes, first in their own right for understanding properties of scattering in asymptotically flat space from a different angle, but then also the aspect that it gives insight potentially into a flat space holographic picture. And so now in the talk here, I will first introduce to you in more detail the change from the momentum basis to the conformal basis, how it gives rise to celestial amplitudes that display conformal covariance, and explicitly give examples for 3- and 4-point amplitudes engaged in gravity. And then for the main part of the talk, I want to describe the double copy relation for these celestial amplitudes by first starting with a revision of the momentum space double copy such that it gets put into a form where we can directly apply it to a setting where momentum conservation is not manifest. And I'll explain in the context of 3- and 4-point amplitudes how this works in the new conformal basis. And then I will end with some comments about extension to all multiplicities and some open questions. I should maybe say at this point that please interrupt me at any time if there are questions, if something is not clear, or if I'm going too slow or too fast.
Hi, Andrea.
Yes.
On that note, I'm going to take that as an invitation for a question.
Very good.
So if we think about, say, pure graviton amplitudes, and we project them onto the celestial sphere, there's this problem that they're, somehow the integrals tell you that you can't look at pure gravity because it's not like UV complete or something like this, yes. Right? So are you telling me that if you take Yang-Mills, which is UV complete on the celestial sphere, in the sense that you can do the
Yang-Mills theory
anyway,
is marginally convergent in the sense that there is some integral that, some energy integral, but this is marginally convergent and it can be interpreted as a distribution. So Yang-Mills amplitudes are fine, but then for gravity, you're totally right. For gravity, the same kind of integrals are not divergent. But if you go to string theory, you can soften this divergence. So in string theory, the amplitudes are fine. Now, if you want to remain in gravity, there is some notion of how you can regularize these amplitudes. But in full generality, you can just go to string theory and they're defined.
Okay, because I was going to ask if the differential operators you introduce are going to induce this divergence at the same time.
Yes.
And is there some other differential operator that you can introduce that undoes it and makes them fine? I mean, I guess it's whatever would give you the correct string theory amplitudes, including
yes, that's an excellent question. Maybe we come back to that when I show the differential operators, but you're totally right. The ones that I will introduce, since I'm remaining in gravity, what they will do is they will make these integrals that in Yang-Mills theory are marginally convergent. They will introduce some shift in the arguments of this integral such that the amplitude is actually divergent.
Okay, thanks.
And it's a very interesting question to see if one can modify these operators so that you get the string theory answer that has the form factors built in which soften this divergence. Other questions? Okay, so then let me go into the details. So I will, for the purpose of this talk, be considering massless scattering processes. In the momentum basis, where we usually discuss scattering amplitudes, we have the 4-dimensional S matrix described by the momenta of the particles, which can be taken to be described by a scale omega, and then some null vector that depends on the points on the celestial sphere where the particles enter and exit, and then some helicity of the particles, and the sign plus minus that tells us about whether the particles are incoming or outgoing. Now, four-dimensional scattering amplitudes, of course, have to be Lorentz symmetry, and this acts on the celestial sphere at null infinity as a 2D global conformal group. And this has the consequence that the S matrix can be recast as a correlation function of some operators inserted at points Z and Z bar on the celestial sphere, and which are labeled by the quantum numbers under the conformal group, namely the conformal dimension delta and the spin J. Now, in a bit more detail, I will only be considering scattering of gauge bosons in four-dimensional asymptotically flat space. The coordinate vectors will be described by X, and these vectors K are null vectors, so K squared is 0. Now, if I have spin, then there are also some polarization vectors and polarization tensors, and I take the polarization tensor to be given by this product of two polarization vectors. We then have spin 1 wave functions given by epsilon times the plane wave e to the I k dot x, and I will use the Lorentz gauge condition, which says that K dotted into the polarization vectors vanishes. Then similarly for spin 2, we have the polarization tensor times the plane wave, and then in harmonic or the Donda gauge, and we have the momentum dotted into the polarization tensor to vanish. Now, in a bit more detail, it's convenient to use a null vector given by this expression. It turns out that this has some nice conformal properties under SL2Z, which acts on Z and Z bar. And then the polarization vectors are given by derivatives of this null vector Q with respect to the coordinates on the celestial sphere. So a positive helicity particle will correspond to a Z derivative of Q for the polarization vector, and negative helicity will correspond to a Z bar derivative. Now, the gauge condition that I've chosen gives us these properties between the polarization vector and the null momenta, and complex conjugation is incorporated in this way, and then they are orthonormal with respect to the helicity of the particles. Now, I want to go from this momentum basis, but labels are the energy, the helicity, and some points in the celestial sphere, to this new conformal basis, where I now have the position on the celestial sphere and two quantum numbers under the conformal group. And this change of basis is incorporated by an integral transform that goes over all energies from 0 to infinity with this particular function, omega to the delta minus 1. And this is called the Mellin transform. So this takes a momentum eigenstate, e to the I k dot x, to a boost eigenstate, which is given by 1 over minus q dot x to some power, and that's given by this parameter delta, and it comes with a normalization factor in delta. Now, to be totally, to be fully correct, I would have to make this Mellin integral convergent, and I would have to add a plus minus I epsilon prescription. Whether the wave is, or the particle is incoming or outgoing will correspond to whether I have a plus or a minus I epsilon sitting here. But this is not relevant for the purpose of this talk, so I'm gonna omit this subtlety here. Okay, so these wave functions of spin 0, I will denote by phi delta. And then if we wanna go to spin 1 wave functions, we just add the polarization vector, or for spin 2 wave function, a polarization tensor, and we get these wave functions, which I will call V delta. So in this sense, we can go from a basis of plane wave functions to a basis of so-called conformal primary wave functions. And the condition that we have finite energy wave functions here translates to a condition that the conformal dimension delta of these wave functions has to lie on the principal continuous series of the Lorentz group, which means the real part of delta is 1 and the imaginary part is a real number. Okay, so the dimensions of these wave functions is complex, and this is already the first thing that makes them somewhat different or unfamiliar in the context or in comparison with vanilla 2D CFTs. Now, this also gives us a kind of state operator correspondence, which identifies massless particles in space-time with operators of conformal dimension delta and J inserted on the celestial sphere. And while the original momentum basis made translation symmetry manifest, but obscured conformal properties, in this new basis, conformal symmetry is manifest. So let me show this explicitly. So under an SL2C transformation, Z goes to this expression, Az plus B over ZZ plus D with the determinant normalized to 1. So this is just a Möbius transformation. And these wave functions phi delta, so the Mellin transforms of the plane waves, under a four-dimensional Lorentz transformation, and this SL to Z acting on the sphere coordinates. This transforms in a way that we know from 2D CFT as being a conformal primary under the global conformal group, transforming with conformal dimension delta on the principal continuous series and spin 0. Now, moving on to spin 1, it turns out that these wave functions V, which were just the polarization vector times this phi delta, do not by themselves transform as primaries, but we have to add a pure gauge term. So we add a total derivative term. And once we've done that, this full expression transforms as a conformal primary of spin plus or minus 1. Similarly for gravity, we have to add a pure diffeomorphism to this wave function V, and then it transforms as a spin plus or minus 2 conformal primary. Now these terms that I've denoted in blue here, they are very important if one wants to talk about the asymptotic symmetries, so the symmetries of this dual celestial CFT, and if it's how it is identified with the symmetries of asymptotic flat space. But for the purpose of this talk, we will not have to bother with this, so I will just work with the wave functions V delta in the following. So now I have shown you the conformal transformation properties of the external states. The change of basis for the amplitudes now consists in Mellin transforming each of the external states in an amplitude. So if I start with an endpoint amplitude, depending on the scale, the energy omega, and the points in the celestial sphere, I have to do n Mellin transforms for each of the external particles, and then I obtain what's called celestial amplitude. Now on the momentum side, I have some function of these parameters, and then this four-dimensional energy momentum conservation. And in performing these amplitudes, I can use up some of this momentum conservation in order to obtain the so-called celestial amplitude. This transforms as a two-dimensional correlator, as can be seen as follows. So just performing an SL2C Lorentz transformation, again in the Zs and the Z bars, we see that the amplitude transforms as a conformal correlator, where the particles have conformal dimension delta J and spin, conformal dimension delta J and spin J. So this is very much like in a 2D CFT. Here we identified the two-dimensional spins with the four-dimensional helicities. But what's different is, of course, that now the conformal dimensions take these complex values. Okay, so now let me give some examples for celestial amplitudes, focusing on three-point gravity and gauge theory amplitudes for now. So I take two particles to be incoming, the other one outgoing. And I will focus on the MHV sector here for illustrational purposes. So the 3 gluon amplitude is given by this expression in the energies and the difference of distances of points, Zij on the celestial sphere. So this is just a convenient way of rewriting either the spinohelicity expression or the expression in terms of the momenta, so in terms of omega and the Zij's. Now after a Mellin transform, so a Mellin transform in the three external states, I get an expression which takes a rather ugly looking form. But if we just focus for now on what's written in the denominator, we recognize that this holomorphic part of the 3-point celestial Yang-Mills amplitude just takes the form of a 3-point correlation function in CFT, where the exponents are related to the conformal weights under the Lorentz group. Now, the endoholomorphic part, on the other hand, is rather unfamiliar. So this is given by distributions in differences of points Z bar on the celestial sphere. And these delta functions here arise directly from the 4-dimensional energy momentum conserving delta function. So this is just a consequence of momentum conservation. Now, for gravity, the story is similar. So starting from the MHV3 graviton amplitude, we get a similar expression. Again, the holomorphic part of the amplitude looks like a 3-point correlator vanilla 3-point correlator, now with different conformal weights than Young-Mills, of course. And again, the antilomorphic part has these delta functions in them. Now, because the power of omegas in the gravity amplitude is different from the one in Young-Mills, this remaining Mellin integral in red is different. So, as I mentioned before, Young-Mills theory, there's this remaining energy integral which can be interpreted as a distribution. So we have scale invariance, and there's an SL2Z invariant way of making sense of this integral, and it's given by a distribution which constrains the sum of the conformal dimension, or in other words, the sum of these parameters lambda. Remember, lambda is the imaginary part of the conformal dimension. Now in gravity, because this is now a different integral, this integral is now divergent, but it can be softened when you go to string theory. If you want to remain in Einstein gravity, there is a way to make sense of this distribution if you allow yourself to analytically continue these real valued lambdas and make them, give them a shift by an imaginary number. In that way, you could then interpret them again as some kind of distribution. And a priori, you would say this doesn't make sense because lambdas are real valued. All the primaries here live on the principal continuous series, which is delta equals 1 plus I lambda, with lambda real. But it turns out that there exist also wave functions with real conformal dimension. For example, a graviton with dimension 2 gives you the stress tensor, which is something that is meaningful. And so there's this way of making sense of these divergent energy integrals by allowing for some of these gravitons in the amplitude to be specific gravitons with real conformal dimension. But in general, you can make sense of these divergent celestial graviton amplitudes when you go to string theory. Now, one thing that I want to point out is, as is obvious from this expression, is that this graviton 3-point amplitude is just the square of Young-Mills theory. But if you look at the expressions on the celestial side, there doesn't seem to be an obvious squaring relation between the celestial correlators. Now, so much for 3-point amplitudes. Let me now go to 4-point amplitudes. So here it turns out that when n equals 4, the celestial amplitude can be described by some universal factor in the zij's and z bar ij's and the conformal weights, and an expression that depends solely on the conformal cross ratios z and z bar. So these are given by these particular ratios. And again, let's take 2 particles incoming and 2 outgoing. The MHV4 gluon amplitude, which takes this expression in the energies and the zij's. Once you Mellin transform the full amplitude, takes this form where the function f is now given by some particular expression in the cross ratios to some powers. And then and this is expected as for a 4-point CFT correlator. But what is different here with respect to vanilla CFT correlators is that we have this delta function and this delta function constrains the cross ratios to be real. So z equals z bar. And this is rather different from usual CFT. And again, as in the case for 3-point amplitudes, it arises from the 4-dimensional energy momentum conservation. So it's an artifact of momentum conservation. Again, we have this red integral now for 4 particles rather than 3, but it takes the same form. So again, we can make sense of it in terms of a distribution in the sum over the lambdas. The gravity amplitudes, again, takes a similar form. Again, we have this extra distribution flying around. And now this red integral is even more divergent than the 3-point gravity amplitude. So before it was +0, now it's +1. And then as you go up in points, it becomes more and more divergent. But again, as you go to string theory, this divergence can be softened, and you can make sense of these amplitudes. For example, in heterotic 4 graviton, in heterotic string theory, a 4 graviton amplitude, you can make perfect sense of. Again, for the momentum space expressions for the amplitudes, there exists a well-defined squaring prescription that relates the gravity amplitude to the Young-Mills amplitude. Now, at least, there seems to be some squaring going on the celestial side, but it's not really clear how universal, and compared to the 3-point amplitude, there wasn't really a prescription. Okay, so maybe I should stop here and ask if there are questions on this introduction to celestial amplitude and some of its properties. Okay, so now let me go on and discuss the celestial double copy procedure. So, as I already mentioned, the momentum space double copy makes heavy use of the fact that the sum of the momenta is 0. In a setting that lacks momentum conservation, such as is the case for celestial amplitudes, the most natural generalization when computing amplitudes using the usual Feynman rules is by using this integral representation of the delta function that implements momentum conservation. And this procedure was introduced a few years ago by Adamo, Casali, Mason, and Nekovar, where they were interested in extending the double copy to curved spacetimes. And what they found was that when you do scattering on plane wave backgrounds, there exists again a notion of a double copy. But in order to see that, you have to sort of go away from momentum conservation because it's not manifest anymore. And you can conveniently display the double copy procedure by using this integral representation of the delta function. And this is what we're going to use. So since we will be working with this spacetime integrand, so the double copy statement will be a statement about the spacetime integrands. And everything that I'm going to do is essentially algebraic. We can complexify momenta so that we can talk about non-zero celestial 3-point amplitudes. This is something that I didn't mention before, but since 3-point MHV amplitudes are 0 if the momenta are real, there wouldn't be 3-point correlators. But if you complexify the momenta or you go to signature minus plus minus plus, then you can get 3-point amplitudes and therefore also these 3-point correlators. So everything in the following will be algebraic, and so we can be agnostic about the signature of the spacetime. We can allow to complexify. These details will be sort of hidden in the manipulations. Okay, so in order to bring a double copy into a form that we can use it for celestial amplitudes, let's start with how to use this integral representation of the delta function for 3-point amplitudes. So we start with this spin 1 and spin 2 wave functions given by the polarization vectors and tensors and the plane waves, and then some color factors, which are Lie algebra valued matrices. And the 3-point vertex contributions to the amplitudes for Young-Mills theory and gravity are given by these expressions, which I have written in terms of these space-time integrals. So plugging in the explicit expression for the gauge field and the metric in these expressions, we get some nice looking formulae in terms of the momenta and the plane waves. And at this point, we haven't really gained anything, right? We can just integrate these expressions and recover the delta function. But it will be important to leave it in this explicit form when we go to a setting where momentum conservation is lost. Now, what we can do is we can massage the gravity amplitude here, given by this gray expression. And the equivalent of using momentum conservation here is doing several integration by parts. And if you integrate this expression several times by parts, you will find that it takes a rather neat form. And the integrand here is just the square of the Young-Mills integrand. So what has been used here repeatedly in this integration by parts is that partial derivatives acting on plane waves just pull down a factor of the momenta times the plane wave. And in this form, by leaving momentum conservation implicit in this integral representation, we see that the equivalent of extracting the delta function that implements momentum conservation is to consider the integrand, written in red here, after we have factored out the products of the plane waves. So this factor is the same in the gravity and the Young-Mills amplitude. There is the same overall spacetime integration. And so the double copy statement here is really one about squaring the integrand. And we will make use of this fact in the following. Okay, so now on the celestial side, instead of the plane waves, we have these conformal primary wave functions, V. I'm suppressing now all the labels as much as I can because it will not be relevant these are details that will not affect the discussion. So remember that these scalar wave functions, the scalar primary wave functions phi are given by a Melian transform of the plane waves, given by this expression, 1 over minus q dot x to the delta. And the first thing that I want to do is, in order to mimic the momentum space procedure, is to write down how partial derivatives act on these wave functions. So before we had partial derivatives acting on e to the ik dot x, which pulled down a momentum times the plane wave. So here I'm trying to mimic the same. And I've written it in such a way that I can call this expression here k, and this will be, I will call this the generalized celestial momentum, because it just mimics the way that partial derivatives act on plane waves. Now, this is different from the momentum space momenta, because they depend explicitly on delta, and they also depend on x, so they're space-time dependent momenta. Now, I'm gonna try to do just the naive thing to try to double copy the Young-Mills amplitude, which would mean that I just, so this is now the celestial 3-point amplitudes for Young-Mills and gravity, indicated by this tilde here. And it turns out that it just takes the same form as the momentum space amplitudes, where the little k are now replaced by capital K's, and the e to the ik dot x's are replaced by the phi's. Now, the naive thing would be to say, oh, the square of this integrand for Young-Mills theory should be the gravity integrand. But that's wrong. So you can show that if you take the gravity integrand and integrate by parts, you will not get the square of the Young-Mills integrand. And the culprit here is this space-time dependent momentum k. So there's something else that I need to do in order to counteract the fact that by integrating by parts, partial derivatives can also hit this celestial momentum k that depends on space-time. So what do I have to do? So the failure of the naive double copy stems from the fact that momentum conservation is lost. So originally we had that the sum of the momenta is 0, but now the sum of the momenta is given by this space-time dependent expression, and it doesn't sum to 0. The origin of this, or related to this, is the fact that the celestial momenta capital K are space-time dependent, and so unlike for the usual momenta, which whose derivatives are 0, the derivatives acting on the celestial momenta now pull up extra factors of the momenta, and they come with this extra factor. You will get expressions where two partial derivatives act on the scalar conformal wave functions. And these will produce this extra factor of 1 over delta in the amplitude. And this is unlike in momentum space where there is no extra term arising. So these extra factors mean that when you square the Young-Mills numerator, you will get extra terms that are not present in the gravity numerator. Okay, so what to do? So our proposal is that instead of using the celestial momenta in the amplitudes, we should actually promote them to differential operators that act on the scalar wave functions with the particular property that acting on the wave functions, it gives us sort of the eigenvalue, the celestial momenta, but it also keeps track of the particle label. So since they keep track of which wave functions they are supposed to act on to give a non-zero result, these differential operators are different from the usual partial derivatives. Another thing to mention about these differential operators is that they take a nice representation in terms of an operator that shifts the conformal dimension of the particles in the amplitude. So this representation is related to the translation generator of the Poincaré algebra, which also has this e to the d by d delta, but it doesn't have this extra factor of delta. So what I want to say here is that this operator e to the d by d delta, if you act with that on an amplitude for all the particles and then you sum up the results of these expressions, then you will get 0, which just tells you that the amplitudes are translation invariant, that they preserve the Poincaré group. But here we have this extra factor of delta I, so this is not the same as the momentum space generator. And our proposal is that you should act with those differential operators on the scalar wave functions in order to give you the amplitude which has this space-time dependent celestial momenta in them. Maybe there are questions at this point about these operators? Okay, so we're promoting the celestial momenta to differential operators acting on external wave functions. And our proposal is that this implements for you a celestial double copy procedure. So we start with the Young-Mills numerator squared, where we promote the capital K celestial momenta to this operator's calligraphic K. So then this gives us a numerator operator that we square, and this should act on the wave functions that remain as an overall factor in the amplitude. Okay, so now let me explain this in some detail. So from this squaring, there are two types of terms. There are these terms where you have two polarization vectors dotted into each other squared, like so. And you have cross terms, like this. Now, the action of these differential operators on the scalar wave functions will produce for you a couple of terms. And in red are depicted those terms that you don't normally get if those capital K's were little k's and you are in the momentum basis. So you get extra terms. And these extra terms arise from the action of these differential operators. So when two of these differential operators of the same type, of the same label I, act on a wave function, they produce for you these extra terms 1 over delta times the celestial, two factors of the celestial momenta times the wave function. And these extra terms shown in red here is precisely what is needed in order to cancel the extra terms that I mentioned before that arise when integrating by parts. So how does that work? We have the gravity numerator given by this expression where we have acted already on the scalar wave functions to get the celestial momenta. Now let's focus on some particular terms in here, for example, the one that I underlined. If we integrate by parts this term in the amplitude a couple of times and we use the gauge choice, which remains the same in this new basis for the celestial momenta, namely that the polarization vectors started into the momenta vanish, and also the fact that the celestial momenta, just like the momentum space counterparts, are null. Doing a bunch of integration by parts, we see that there's these extra terms arising from integration by parts. And there is extra terms that arise when you have, for example, the polarization vector epsilon1 dotted into K2 squared or into K3 squared. And if we look back at the previous slide, those were precisely the extra terms that show up when squaring the Young-Mills numerator. So this slide was about squaring the Young-Mills numerator. It produced extra terms. But if I go to the gravity amplitude and I integrate by parts, I produce the same extra terms. And so this means at the end of the day, if I do this for all the terms that show up in the gravity numerator, I integrate by parts enough times, then we will find that this gravity numerator operator acting on the scalar wave functions is precisely given by the Young-Mills numerator operator squared acting on the wave functions. And so here we have shown that there is a celestial double copy between 3 gluon amplitudes and 3 graviton amplitudes. Are there any questions at this point before I move on to 4-point amplitudes? Okay, so 4-point amplitudes, a bit more challenging. So for the 4-point Young-Mills amplitude, we have essentially contributions from the 3 channels, S, T, and U, which depend on points X and points Y, and are related by a propagator. And this propagator has, we take this propagator to take the usual form, where the indices mu nu are just implemented by the metric eta mu nu, and then some function which takes the usual form for a propagator with momentum k. Now this propagator satisfies the fact that acting with box with respect to derivatives of x or with respect to derivatives in y, is just given by the four-dimensional delta function in x minus y. Now, this fact we use in order to open up this contact term contribution to the 4-point amplitude, such that it also depends on x and y, but of course, this is only a way to rewrite it using this four-dimensional delta function. So the procedure here is to open up this contact term such that it has contributions to the S, T, and the U channel. And then after a bit of massaging and using these properties of the propagator, we get that the 4-point Young-Mills amplitude can be written as the following space-time integral. So here we integrate over the points x and y, this propagator function here. And then there are three contributions. And let me unpackage what this means here. So these capital phi's here are just the plane waves in the S, the T, and the U channel. The C's here are just the color factors, which satisfy the Jacobi identity. And the N's here are the kinematic numerators that I mentioned in the very beginning in the motivation. And so, for example, for the S channel, this takes this rather horrendous looking form in terms of the momenta and the polarization vectors. So this is the Young-Mills amplitude in the momentum basis. And we can, where we have, instead of writing momentum conserving delta function, we have written these explicit space-time integrals. So in order to show that you have color kinematics dual numerators, instead of using momentum conservation, as I did in the very beginning in motivating the double copy, we now use integration by parts and the fact that the propagator satisfies this condition, that x derivatives acting on it is minus y derivatives acting on it. So, okay, we have this nice expression for the Young-Mills amplitude in a form where we don't necessarily use momentum conservation explicitly. Now, in order to go from this 4-point Young-Mills amplitude to the 4-point gravity amplitude, what we do is we replace these color factors by another set of kinematic numerators, and then on the nose we have the 4-point graviton amplitude. Okay, now I want to rewrite this whole thing now in the celestial, in the conformal basis for celestial amplitudes. So, okay, before doing that, maybe let me just stress again that what we have done here is we have stripped off the integrand of all these wave functions, of all these plane wave functions. So this is an overall factor in each of the channels between Young-Mills and gravity amplitudes. And we have a common propagator. And then the statement of the double copy is really about the integrands, the numerators in the integrand. Okay. So now we want to perform a Mellin transform on these 4-point amplitudes to get the celestial amplitudes and see how the double copy works there. So effectively what we do here is we replace these wave functions, the plane wave functions e to the I k dot x by wave functions phi j and the momenta little k by the momenta capital K. And so then the celestial Young-Mills 4-point amplitude, which I've given to you before explicitly, where we used momentum conservation and we got all these delta functions that were rather odd looking as far as 4-point correlators into a 2D CFT is concerned. Now we don't want to do that. We don't want to use the delta function, we just keep this integral representation of it. So then we get an expression that very much looks like the one in momentum space. Now this capital phi tildes are given by the conformal primary wave functions rather than the plane waves. The C's are still the color factors, and the kinematic numerators now are given by similar expression where the little k is replaced by capital K, but now these depend explicitly on the positions. And not only do they correspond on the positions, but they depend on different points x and y. And this gives a complication that one has to carefully deal with when massaging the amplitude to implement the celestial double copy. Okay, so now similar to the 3-point amplitudes, just replacing the color factors by another set of kinematic numerators does not work. And the reason again is that there are extra terms in the amplitude which arise from the fact that we have now space-time dependent numerators. So the prescription is as follows. Instead of working with this space-time dependent celestial momenta k, we replace them replace them by these differential operators calligraphic K. Okay, so now we have a celestial Young-Mills amplitude where these n's here are now operators acting on the wave functions phi. Then the next step would then be to replace the color factors by another set of these operators rather than the numerators. And so we get an expression where we have some numerator operator squared in each of the channels. And the question is, does this correspond to the celestial 4-graviton amplitude? So here we started with the celestial 4-point Young-Mills amplitude. We replaced the celestial momenta by differential operators, which turns the numerators into operators. And then we replace the color factors by another set of numerator operators. The question is that the Mellin transform of the 4-graviton amplitude? And to check
Andrea, can I just ask something quickly? Just by way of clarification, squared in this context will then mean 2 actions of the operator on the wave function.
Yes, precisely. Okay. So like I wrote in this expression here, 2 of these operators acting on the wave functions.
Okay.
Okay. Good. In order to check that this is true, we need to use some properties of the Mellin transform. So let's go back to the original 4-graviton amplitude, and let's write it in a way that makes the double copy manifest. So for the 4-graviton amplitude, we have this numerator squared, which depend on the momenta little k, which were space-time independent. And the capital phi's here were just the plane waves. Now, this expression depends on the energy of each particle, so the zero component of this momenta k, in a polynomial fashion. And when Mellin transforming that expression, so meaning that we have 4 integrals in the energy, there are 2 cases that arise. One is when the numerator has a linear dependence in the energy, so there's 1 factor of k. And the Mellin integral of this expression, where we have k mu times the plane wave, is just given by the celestial momentum times the conformal primary wave function. The other case is when the numerator appears quadratic in the energy, so the Mellin transform of this expression is now given by 1 plus 1 over delta times 2 factors of the celestial momenta times the conformal primary wave functions. But this last line is precisely the way, well, both of those is precisely the way that these operators calligraphic K act on the wave functions, which I just showed you when Jeff asked the question, where you have 2 Ks acting on the wave function. It precisely gives you this 3 factor, 1 plus 1 over delta, and 2 factors of the celestial momenta. And so because of that, the fact that the Mellin transform of these 2 expressions which show up when you try to go from the 4-graviton amplitude to the celestial amplitude, the fact that this is mirrored by the action of this calligraphic case tells us that the Mellin transformed 4-point graviton amplitude is precisely what I've written on the previous slide. Namely, it's given by a square of the Young-Mills numerator operators acting on the conformal primary wave functions. So this shows that for the 4-point amplitude too, there is a double copy prescription in for the celestial version of the amplitudes. So let me just recap this. So we started with 4-point Young-Mills amplitude, where we didn't use explicit momentum conservation. We left these space-time integrals. We used some properties about the propagator to massage the expression in this nice form. Similarly, for the 4-graviton amplitude, there we know that there exists a double copy because we are still in momentum space here, and the ends don't depend on the space-time points. Now then what we did is we Mellin transformed, and we replaced these Mellin transformed numerators by operators, both for Young-Mills and for gravity. And that gave us the Mellin transformed Young-Mills and gravity amplitudes, which have now operators acting on the scalar wave functions. And as you can see, the double copy consists then in replacing the color factors by another set of numerator operators acting on the wave functions. Okay, so very nice. We have a celestial version of the double copy for 3-point and 4-point amplitudes. And what's more is that the fact that we have these celestial momenta promoted to operators gives us a nice representation for amplitudes, because we can now write a Young-Mills amplitude, so here Young-Mills 3-point amplitude, as a scalar amplitude where we have an operator acting on the scalar amplitude to give you the Young-Mills amplitude. Similarly, the square of this operator acting on the scalar amplitude gives the gravity amplitude. And this persists to 4 points and higher points. So for 4 points, we rewrite this whole expression, which contains these integrals in x and y and the propagator. We rewrite them in such a way where the s, the t, and the u that's written in this, I don't know, MACFRAC version is explicitly dependent on the conformal dimensions of each of the external particles and is given by this integral of scalar conformal primary wave functions. And the 4-point Young-Mills and gravity amplitudes are then obtained by the action of these operators that I previously wrote down for the ST and the U channel, acting on these scalar amplitudes in the ST and the U channel. Okay, maybe there are questions before I make my last comments and pull up some open questions.
Yeah, so you said that you're acting on scalar wave functions, right? So does that mean that you expect this to hold if you have something like bi-adjoint scalar fields? Do you expect those to square all the way through?
It seems that here, at least, once you promote momenta to operators, everything nicely goes through so it mimics the momentum space structure. So I don't see a reason why one cannot see what, if you square the bi-adjoint scalar, that you should get the Young-Mills.
Okay, thanks.
So this, maybe a comment here. So this version of promoting this momenta to operators, it's, yeah, okay. Maybe I'll come to that on the last slide where I have some comments related to that. Okay, if there are no more questions, let me make maybe some last comment before I conclude. So I didn't have time to talk about loops, but this representation of amplitudes as operators acting on other amplitudes, in this case, some higher spin amplitude is given by an operator acting on some lower spin amplitude. So this structure of having operators acting on celestial wave functions, celestial amplitudes, there is a version of that also for going from tree level to loops. So consider, for example, n equals 4 super Young-Mills and look at 4 gluon amplitudes in the MHV sector, in the planar sector of n equals 4 super Young-Mills. So there you can get the all loop amplitude. You can put this in this convenient form where you have the tree level amplitude and then some factor here, which is a summation of all the loop amplitudes. And what's nice in n equals 4 super Young-Mills is that this resumming of all these loop factors exponentiates and gives the so-called BDS formula, where you can get the all loop amplitudes as an exponential factor times the tree level amplitude. Now, if you try to Mellinize this and get celestial amplitudes for gluon processes in plane of n equals 4 super Young-Mills, what you will find is that the all loop celestial amplitude can be expressed as an operator acting on the tree level amplitude. So this factor for this L loop factor ML gets replaced by an operator that acts on the tree level celestial amplitude. And this operator so here this is done in dimensional regularization where epsilon comes from v equals 4 plus 2 epsilon. And so this operator, which replaces this L loop factor, depends on a function of the cross ratios, which, okay, here I denoted it by R, but it's the cross ratio Z that I showed before. It's infrared divergent as you take epsilon to 0. But then there is an operator p hat to the power L epsilon, where L is the loop order. And this operator p hat is somewhat related to the celestial operators that I showed before. Namely, they also have a derivative with respect to the conformal dimension, or with respect to these lambdas. So, and one can also recover a resummation of these celestial L-loop operators to give an all-loop operator acting on the scalar amplitude that is an exponential, well, it's actually a double exponential operator in this derivative with respect to the conformal dimension. So also, if you go to loops, there is this statement that you can express them as operators acting on tree-level amplitudes. And it's a similar kind of operator that shows up in this story. But this is an aside that I wanted to mention because it resonates with the presentation of amplitude that arises in this celestial double copy procedure. Okay, so with that, let me conclude. So I showed to you a celestial double copy procedure and explicitly displayed this for 3 and 4 point celestial amplitudes, but it naturally generalizes to higher point amplitudes. Instead of having these two spacetime integrals in x and y, we now rewrite the amplitude in terms of n-2 spacetime integrals, and then we open up the contact term, much like what I did before in the S, T, and U channels by using the properties of the propagator. And then again, we promote the celestial method to differential operators and let them act on the external wave functions. Okay, then there's a question. So I showed this explicitly for gauge theory on gravity at tree level. What happens if you go beyond tree level? What happens for other theories, as was already mentioned? Is there a celestial double copy procedure in other settings? Another question is whether we can get constraints on these differential operators in the celestial amplitudes via our generalization of the color kinematics duality. And maybe this can shed light on the kinematic algebra by working in this celestial setting. Then there's a question of what's the best way to actually represent the celestial double copy. And a comment relating to that was already made. Here, what we find here is very reminiscent of recent results by Sebastian and company, where about ambitwister strings in ADS spacetime, where numerators are given by operators which seem to obey an operator version of the double copy. So this is what we find here, that you promote these numerators to operators acting on wave functions is very reminiscent of this recent work. And it would be interesting to study in more detail. There's another setting where ambitwister strings have been used to discuss celestial amplitudes, and that's in the context of conformal soft theorems, where it seems a convenient way to find all the factorization properties of celestial amplitudes by working with ambitwister strings. So it would be interesting to study this direction further and understand what's the best way to write down celestial amplitudes and display some of the fundamental properties. Okay, thank you very much.
Thank you very much. Does anyone have any questions? I guess you've answered all of our questions during the talk. Okay, well, if no one has any questions, I'll just thank
Actually, I have
again.
not really a question, but kind of an observation. So I think it's quite neat the way you packaged how the double copy works in terms of the color factors and the ends. I like that presentation. It's quite neat that you can see where each of the, so it's one thing to say that the double copy, the bumper sticker for the double copy is Yang mil squared. You get gravity, but it's nice to see it in the replacement of the C's with an N and the N's with an N.
Yeah, and it also one motivation for studying the double copy in the celestial amplitudes is because it lies somewhere in between the flat space amplitude double copy in the momentum basis, and where you use explicit momentum conservation, and the double copy in plane wave backgrounds, or more generally in curved backgrounds. because it's still, it has the complication that you cannot use momentum conservation, but it's in some sense simpler or nicer than general curved backgrounds. And the fact that you have these operator statements connects to more, well, it connects to these ambitwister strings, and maybe helps to use some methods developed in ADS in order to understand better this speculative 2D celestial CFT.
Hi, Andrea. Thanks for the talk. Can you repeat what do you think the best strategy for proving the higher point double copy is? What's your idea to do that?
I would just mimic what we did for 4 points here. Again, okay. Well, compute first the celestial amplitudes. Okay, so this is, yeah. So for Young-Mills, celestial amplitudes have been computed to n points by the Rubel-Brown. Well, okay, let me say this. So once you use the momentum conserving delta function and you compute celestial amplitudes such that they look like correlation functions, this becomes harder the higher you go in points, because for lower points, you have delta functions that you can use to perform the integrals, but then as you go in higher in points, you actually have to do some work. But there exist expressions, but we don't want to do this here because we don't want to explicitly use the delta function. So I would just really use this representation, and when you try to Mellinize the higher point amplitudes, use this fact that I think the momentum little k should again be, so the celestial version of higher bound amplitude should again be given by a similar expression in momentum space where the little k's are replaced by capital K's and the plane waves by phi's. And then I think the story should just go through in the same way. You replace all the capital K's by the operators, and then you square that and you use a bunch of integration by parts. Is there a reason what should go wrong, or?
No, it just because you have to use IBPs a lot of times, it's not prescriptive how to do that, to massage things to trivalent diagrams. And I guess that's the analogous procedure of what you would normally do by, splitting contact terms into trivalent diagrams. But I was thinking more, there's some consistency checks that you can make on your tentative squared amplitude, like checking OP limits or these conformally whatever soft theorems. So maybe you can use something like that and say that once all these are satisfied, then you probably have the right answer. I don't know. Is that?
You mean because it's very tedious to do all the integration by parts to explicitly show that the squared amplitude is the right answer?
Oh yeah.
Maybe there's a set of, a finite set of consistency conditions that have the unique, that uniquely tell you that this must be it, there's no other option.
That's a question.
Yeah, that's a very interesting question. Yeah, I have not looked at higher points explicitly, but yeah, you're right. It becomes very tedious, and
another way, presumably at tree level, you would be able to set up some kind of a recursion relation on shell or off shell. Maybe that would be a way of like somehow recursively proving your formula.
Yeah, so this recursion relation have been shown for the correlators. Well, once you use the momentum conservation, but in this setting, we would just use the momentum space once and leave the integrals. Yeah, that's a good point.
And have you studied at all an analog of a KLT formula for correlators?
No. Yeah, that's a very interesting question. String amplitudes in this setup have not been.
Oh, I meant the KLT formula for field theory.
Yeah, I haven't thought much about it.
Yeah, okay. Presumably it can be built out of these kind of curly K operators as well.
Right. Yeah, well, that's of course a natural thing to look at. Yeah, but I haven't done so.
Okay, thank you.
Yeah, it would be nice to put this in more in a form where you can use the scattering equations. And so this is why I said before that ambitwisted strings is maybe more suitable to describing the celestial double copy. Yeah, there are many questions that many things one can look at. Yeah.
Does anyone else have any other questions? If not, thank you again, Andrea.
A pleasure.
And see everyone next time.
Yeah,
Thanks a
stay
lot.